What percent of this entire bin is red? 8? 80? 70? Are you guys with me that just staring at this and trying to make that conclusion is an unpleasant idea? Yeah? So what if I say take a sample and I were to tell you that 18 out of the 22 beads in this sample were red? Would that help us start to make a guess? So we're good? You guys, we got a problem because this one it's only 16 out of 22. Is everybody with me? First it was 18 out of 22, then it was 16 out of 22, 17 out of 22, 16 out of 22. I'm just counting, by the way, I'm not counting the reds, I'm counting the non-reds. And subtracting, yeah. But you guys get the basic premise of this, yeah? So when I take a sample, so we had 18 out of 22, we had 16 out of 22, we had 17 out of 22, we had 16 out of 22. So will I always get the same percent red from my sample? So if what I'm talking about is the percent, the sample's not all the same percent. What about the percent of the bin that is red? Is the percent of the bin that is red always the same number? It just exists somewhere, right? We don't know what it is, but it is only one value, yeah? So when I say will it always be that percent? The samples will not always have the same percent, but the population always has the same percent. Does that feel okay? And is it possible that I take every single possible sample out of here? Theoretically. Are you guys with me that that is an unreasonable thing to do? Okay, great. Because there's actually more samples than there are beads. Yeah? Okay. Now, is it possible? Yes. But not realistic. So what we're going to start to do is think through what we call it, something called a sampling distribution. And I won't expect you to know what a sampling distribution is until we get back from Thanksgiving. But I want you guys to envision kind of like, could I make a graph of all of these numbers and then imagine I did those percentages over and over and over and over again for every single possible sample. Okay? Great. All right. So before we can really get too far into sampling distributions, I do want us to think through, we're going to rely on the normal distribution and the thought processes behind knowing something is normally distributed and what that means. We're going to be going through that a ton. So I want us to be in a place where we can kind of think through and review those ideas, okay? So the weights of hazelnuts are normally distributed with a mean of 1.34 grams and a standard deviation of 0.25 grams. Okay, so if I have a hazelnut that weighs 1.56 grams, what does it mean when I say what is the z-score? What did the z-score really mean? Is a number of standard deviations from the mean. So, will this hazelnut have a positive or a negative z-score, and how do you know? Positive because it is bigger than the mean. So, we could say how far above the mean is it? And then how many standard deviations is that? So a reminder, the formula for z-score is the observed value minus the mean divided by the standard deviation.
Mean is mu, right?
Mm-hmm. As your population mean is mu. We'll talk about that in like 10 minutes. .88. So we could say that hazelnut is 0.88 standard deviations above the mean. Again, the word above or below, kind of important, because we're basically describing. So is that a super big hazelnut? How many standard deviations above the mean do you need to be for something to be kind of like super crazy? It was 2 standard deviations. So I would not call this a super big hazelnut because it's not even a whole standard deviation. It's big, but it's not like crazy big. Cool? All right. Weight is the 30th percentile. Yes, what does it mean to be the 30th percentile?
Isn't it like they're going to be like 70% of population is going to be larger?
Okay. I'm going to just say it is 30% would be lower. Yeah? Which tells me that this area is 0.30. Do you guys remember where in the calculator we can find this? Inverse norm of 0.3. It's actually, that's meant to be that mu symbol. Like, it's a pixelated cursive M, basically, for the mean. But it's because it's pixelated that it's not very good. That feels reasonable to me. 1.21 grams, yeah. Are we all getting 1.21? Everybody feeling good? All right. What range of weights contains the middle 90%? I don't know if we've done much with this kind of thing or not, but So let's start with just drawing where the middle 90% are. If I have 90% in the middle, we're going to start really talking about tails. Okay, we have a right-hand tail and a left-hand tail, right? This is the right tail. It's the tail of the larger values. The left tail is one of the lower values. And what do I know about the area of both of those tails combined? What does it need to be? 10%, right? So what does each of them individually need to be? 5%. So because normal distributions are approximately symmetric, we can assume they're the same. So just divide that 10% in 2. Yeah? Okay. So then what do we tell the calculator? In some respects, like if I want to find this specific value here. Do I know the area to the left of that specific value? It is 5%, yeah? And after that, it's no different than the picture above. We're going to do the inverse norm of 5%. And let's see, give or take 0.88, 0.932. And then this value, what is the area to the left of that value, of the upper one? You guys with me that it is 95%? Because it's the 90% plus the 5% tail. Now, some of your calculators allow you to just put in 0.9 for the center. That's just fine. Just not everybody's calculator does that. So I want to go through the... what are we getting? 1.75. So we would say between, the interval would be between 0.932 grams and 1.75 grams. Okay, new context. The running times of movies are normally distributed with a mean of 102 minutes. At 92 minutes, Aladdin is the 23rd percentile. We want to find the standard deviation. So in this case, for right now, if I don't know the mean and both the mean and the standard deviation, using that function on the calculator doesn't work. So does anybody remember what we did here? We did have some questions like this. Yeah, we can find, because we do know the mean and standard deviation of z-scores. Z-scores always have a mean of 0. They always have a standard deviation of 1. So we can find the z-score associated with the 23rd percentile. And again, knowing something, we need to know it's normal in order to do this, but we can do it. What is the z-score of the 23rd percentile? Negative 0.74? Great. And picture-wise, guys, that means that this distance is 0.74 standard deviations, which also means then that this distance has to be 0.74 standard deviations. Is everybody comfortable with this idea? What is this distance? Like, if I don't think of it as the number of standard deviations, if I look at it on the axis, what is this distance? 10 minutes, yeah? Okay, so I have 10 is equal to 0.74 times the standard deviation. I'm just imagining 1.3 and some change. 1.33? 1.32 maybe? No. 43 and some change. If I do 10 divided by 0.74.
I got 13.5.
13.5. Oh, yeah, okay. Now, if you want to use the z-score formula, guys, we could say negative 0.74. Like if you're more formula-based, the z-score is equal to the 92 minus the 102 over the standard deviation. When you solve this, you're going to end up with the statement 10 equals 0.474 sigma. Like you'll end up there. Okay, so if it's easier for you to think through, I know my z-score formula and go from there, that's fine. All right. Good so far? Fantastic. All right. Now, for pretty much the entire second semester of the course, we're going to be dealing with what we call statistical inference. When you guys hear the word inference, what does that mean to you?
Educated guess or assumption.
An educated guess, great. In statistical inference, how do we educate our guess? We take a sample and use it to make a conclusion about a population. Okay, so statistical inference is using a sample to conclude about a population. And there's lots of different types of conclusions we can make. Okay, so we're going to learn lots of different techniques for statistical inference. All of Unit 5, where we're going from here, all of it, the goal will be laying the groundwork for the thought processes behind the statistical inferences that we will be doing. Okay? So, there's some new vocabulary I want us to start thinking through. Okay? All right. So, in the statistical world, we have parameters and we have a statistic. Okay. A parameter is a number that describes the population. For example, what percent of this bin is red? That's a population. We would use a number to describe it. Could I ask you guys, could we find the mean weight of all the beads in this thing, right? Like if we had a super fine scale, put this on it, I could get the weight of this one, and then this one, and this one. You guys catch my drift here? Right, we could so we have a population mean. Now, a statistic is very similar, except for it is the same number, but it describes a sample. So, for example, when I take this sample, that is 16 out of 22, that is a statistic, because it's a percent of red here, percent of red of the sample is a statistic, percent of red of the bin, the entire bin, is a parameter. You guys catch it? Okay. All right. So, a parameter, one of the things I want us to understand is some sort of unknown constant. So when I said there's only 1% red in here, right? This bin only has a specific, there's only one percentage that describes what percent of the entire bin is red. Okay? Whereas the statistic is a known variable. Calculating the statistic is easy. You take your sample and you calculate it. Okay? We know what it is. Unfortunately, different samples have different values. Okay, so it's a variable. It changes depending on which sample I take. I take a new one, different percent. New one, different percent. Okay, so the percent for each sample is variable. Is everybody with me? But it's known. The percent of the bin stays the same, but it is unknown. Everybody good? Okay, so we have been dealing with some of this already, but I'm going to kind of formalize stuff now, okay? For example, earlier someone asked what the symbol on our calculator was, and I said it was mu, a curly QM, that describes the population mean, okay? So if what I'm measuring, if I have a mean and it's of the entire population, we call that mu. That would be the symbol we use. If I have the mean of a sample that is not from a population, we use the symbol X bar. So X bar is a statistic. There are a lot of different X bars for a population. Mu is a parameter. There's only one mu for a population. This is the actual mean of the population. Again, usually unknown. Okay. Likewise, sigma, and S is the one we use off of our calculator, right? When we describe normal distributions, we're describing the population. That's why we use mu and sigma. But when we think about what we grab off of our calculator when we have a sample of data, we use S and X bar. Okay? All right. Now, we haven't talked about the parameter and statistic we were modeling here, which are proportions. Remember, proportion is the decimal version of a percent. Okay? So, the proportion of a population is P. The proportion of a sample is P hat. All right. Gallup poll asks a random sample of 515 U.S. adults whether or not they believe in ghosts. Do any of you guys believe in ghosts? Yes? No? Interesting. Usually get at least one or two. Okay, so what population is this sample trying to describe? What is my sample?
515 adults in the U.S.
The 515 U.S. adults, which we were told was randomly drawn from all U.S. adults. So my population would be all U.S. adults. What's my statistic? What do we know about our sample? So we would say my statistic is P hat, 160 out of 515. So you guys got 31%, 0.31. And what that P hat is trying to estimate is what P. I'm going to be very particular about when you describe what a parameter is. We're going to call it the true proportion of U.S. adults who believe in ghosts. Everybody good? True proportion meaning like we don't know that it's 31%. 31% is that one sample. The true proportion is the one we don't know, that we're trying to estimate, that we're using our sample to get to that estimator. All right. What if I had a random sample of 318 teenagers who had a mean screen time of 4.5 hours? What's my sample?
318.
The 318 teens. Who are they trying to represent?
All teams.
All teens. What's my statistic? I'm going to call it X bar because it's a sample mean. What was my sample mean? 4.5 hours. And my parameter would be mu, the true mean screen time for teenagers.